In this video, we're just going to look at some top tips to help you really get the most out of your chemical calculations, quit making some silly errors. This is not going to be a video going through how to do every type of calculation. There are loads of those. This is just looking at ways we go wrong and ways that we can really improve it. Either whether we're starting from GCSE and heading into A-level, or just wanting to get the best marks at GCSE, or we're in the middle of A-level and perhaps we've still got some bad habits or some things we haven't thought about. Okay, so tip number 1 is to get rid of this. Stop using formula triangles. So I'd really hope that if you're in the middle of A-level, you're not using these anymore. They are really a crutch. They're useful when you start doing calculations, maybe, to just take some of the load off your brain while you're trying to get to grips to it. But you do far more complicated maths in GCSE maths than you do involving 3 things. And there are just so many equations that you can't use them for. So you need to know how to rearrange formulae that have more than 3 things in them. So this is very common in the first year of chemistry. Very common in the second year of chemistry. If you haven't come across it yet, you're going to have to be able to rearrange this equation. So now you need to know not just how to divide things that have been times or add things that have been taken away. Now you need to know what the inverse function of things like logarithms are. It's all on the calculator, but formula triangle is not going to help. And it's not going to help where you've got different terms that are separated in different ways in equations. So don't need a formula triangle. You know full well how to make things the subject of equations. Do some practice, go back over some of the maths you already know and see where it fits in with the maths that you're coming across in chemistry, because the maths you come across in chemistry is never as hard as the maths you do in a straightforward maths subject. Understanding units, so this actually doesn't really come up so much in maths, maybe at A-level. At GCSE, we definitely talked about concentration, and it was nice and clear, the units. So we had the units written out. They told us what to do. So this is where we don't need a formula triangle, and we don't need to rote learn calculation for concentration, because the calculation is right there. Concentration equals moles divided by decimeter cubed. So the sign is there. At A-level, we don't write it in such a clear way, so or it doesn't seem as clear. So what I want you to do, though, is when you see that unit, is to say it, moles per decimeter cubed, and don't say mole dm minus 3. If you don't understand what you're doing there, that's when people forget why the minus is there, because it means 1 over, and they get really, really confused. Another one, which was written more clearly at GCSE, would be kilojoules per mole. Again, say it, kilojoules per mole. That tells you exactly how to do an experimental delta H calculation. Once you've got kilojoules, once you've got number of moles, it's kilojoules divided by moles. And then something that's maybe not quite so obvious, but especially because we tend to just look things up, like specific heat capacity, and we tend to just get the number and not look at the unit. But if you look at the unit for specific heat capacity, it's telling you what it means. It's actually telling you how many joules is needed per 1 gram, so per gram, per degree Kelvin. So it's telling you that if I had 20 grams and it raised the temperature by 10 degrees, if I times that value, the specific heat capacity, by the grams and the degrees, I'll be left with joules. So it tells you how to rearrange the equation. So that's units. Estimation, something else we do in maths that we don't do so much in chemistry, especially because we're not really familiar with the amounts that we're using, because we don't use chemistry amounts anywhere else. Unlike physics, where we use meters and seconds and kilograms more often, in chemistry it can be that we just get, it seems very detached from the real world, but you do plenty of experiments, so you do have a good idea about some sizes of numbers. So relative formula mass, you know that that comes from the periodic table. It's not going to be a number in standard form. it's not going to be a number any less than 2. So the absolute minimum of any mass you can have for an element or a compound is 2, H2. So that's like the smallest mass we can have, and it might go up to about 200. Maybe if you have a large metal, a heavy metal atom in there, maybe if you have a complicated large organic molecule, or a hydrated salt, so something that's got maybe 10 water molecules added onto it, that would have a larger mass. But if you're getting a relative formula mass of 5,000, unless it's a polymer or a very large, what we call a macromolecule, sounds like you times instead of adding, so you can spot your mistake. Energy change calculations. Can you tell if it should be a plus or a minus? That's not really about the size, but it's a really important one, especially because you're not just going to do delta H. In the second year, you're going to do some other values, delta S, delta G, potentially. So you have other values and you need to know what's a sensible size and what's a sensible sign. So how big of an energy change it is. We do lots of standard enthalpy changes that we look at. Combustion should be in the thousands for a hydrocarbon or an alcohol, maybe high hundreds if it's very small, like methane. Smaller energy changes are things like room temperature reactions, things that happen naturally, like acid-base neutralization or anything you're doing for a rates experiment. Bond energies, covalent bond energies, pretty large, and if you've done lattice energy yet, you know again that that should be really, really large. So lattice enthalpies should be in the thousands. Formation enthalpies for making compounds, again, they're usually in the hundreds. They're not huge. Number of moles. So again, something that we detach from and we never know. Is that a sensible number of moles? I don't know. It's just number of moles. It's not something I count in everyday life. But we use it a lot in chemistry and it's going to be small if it's a practical question. We don't normally handle a whole mole of anything in chemistry, like maybe water, because that's only 18 grams of water. But thinking of other substances, calcium carbonate has a formula mass of 100. You've never sat and weighed out 100 grams of marble chips. Magnesium has an atomic mass of 24. We've not ever used 24 grams of magnesium in an experiment. That would be like, I don't know, about a third of a whole reel of magnesium. So we're never going to use that much, which means when we do calculations, moles for normal experiments that we're carrying out ourselves should be small. Only exception, industrial chemistry questions. So now we're talking about large amounts, perhaps we're talking about kilograms or tons. Obviously then, that's going to be a large number of moles. And then in titration calculations, this estimation idea is really useful. So whether the size is right, whether it's the right magnitude. So thinking about equipment for titrations, a burette holds 50 centimetres cubed, pipettes hold 10 or 25. So we shouldn't be ending up with a titration volume of 150 because that would involve filling up the burette lots of times. Occasionally we might titrate a larger volume if it's very dilute, but that's unusual. Normally we use standard flasks, standard pipettes, and therefore our volume, if I need 25 centimetre cubed of one thing, it's really unlikely that I'm going to need, say, 300 centimetre cubed of the other. And then concentrations of the thing that we know the concentration of and the titrant, the thing that we don't know, they shouldn't be vastly different either. Titrations should be kind of done so that if the volumes are the same magnitude, the titrations are the same magnitude. So if you have an acid and a base reacting together, 20 centimetre cubed of one and 20 centimetre cubed of the other, then you know they are roughly the same concentration, unless they are 2 to 1 or 1 to 2 in the balanced equation. Then you have to work it out. Either way, they're not going to be 10 or 100 or 1,000 times the concentration. Anytime you see anything that seems like it's 1,000 times wrong, 1,000 times too small or 1,000 times too big, obviously go back and check somewhere you've probably forgotten a unit for volume. You've probably forgotten to convert decimetre cubes or centimetre cube. Number 4, significant figures and decimal places. So if you haven't seen it yet, you're going to get questions that ask you for appropriate significant figures, and you're going to get questions that ask you to write perhaps result values down or fill in a table, and you're not going to get clues like you do at GCSE to tell you how many significant figures or decimal places. Sometimes at GCSE you don't get the clues. So when should we use one and when should we use the other? Well, let's consider an energy change experiment. So taking a large glass kind of spirit burner with some alcohol in it, probably all done that experiment. You weigh the spirit burner with the alcohol in. You use it to heat a set volume of water. You measure the temperature at the start, temperature at the end, and then you re-weigh the container of the alcohol afterwards. So you might get a results table that looks like this. So if we look at the mass readings, we weighed the spirit burner at the start and at the end. Now they're quite heavy, and the decimal place of the scales in this case was 2 decimal place balance. So it sort of looks like, if we were just to take significant figures, it looks like the mass is actually being recorded to 5 significant figures. But that's not the number that we're using in our calculation. We're using the mass burned. And so in this case, it wouldn't make sense to say, let's record the mass burned to 5 significant figures because that's what the burner is recorded to. So I wouldn't write 2.0000 because my balance doesn't read any more than 2 decimal places. So by writing 2.00, I'm saying that I know that my margin of error, I know the value is somewhere between 1.995 grams and 2.005 grams. It's somewhere in that reading, plus or minus 0.005 grams. So that's why we put the 2 decimal places on, because that's the level of accuracy of the balance. I wouldn't just write 2, because that means, I don't know, it's somewhere between 1.5 grams and 2.5 grams, which is a very, very broad range of readings. Okay, so in this case, decimal places make sense, and the same for the temperature change. So that's a thermometer that can read to 0.5 degrees, so I would put 0.0 or 0.5, and then that is to 3 significant figures. So when I take those 2 values and I put them into a kilojoules per mole calculation, so I'm going to work out the moles from the mass burned, I'm going to work out the kilojoules from the temperature change and the volume of water, then how I decide about my final answer, it doesn't make sense to use decimal places, because my final answer is probably going to be like maybe 1,000, 2,000 kilojoules. So I don't want to put 2 decimal places on that. That becomes a 6 significant figure number, which is way more accurate than my data that I put in. So when I'm deciding appropriate significant figures, I go for the smallest amount of significant figures in the information that I use to calculate it. So in that case, both of these numbers are to 3, so I would use 3. I'm not using 3 just because we always use 3. If I had a 1 decimal place balance, then I would have to do it to 2 significant figures. So if I just had 2.0. Alternatively, if I weighed a very small mass, like 0.86 grams, that is now 2 decimal places still, but it's now 2 significant figures, 0.86. So I would have to do my final answer to 2 significant figures. And then the last thing seems simple, but a lot of students don't do this, especially when you have a multiple choice question. A lot of people just dive in, have a guess, instead of trying to work it out. Or when you get a large question, which is maybe 3, 4, 5, 6, 7, 8 marks, who knows, they're going to get longer the more you do them. So a lot of people just don't want to write stuff down. So one of the reasons might be that you're worried that you're going to go wrong and mess it up, and you just kind of want someone to tell you where to start. The more you do that, the more you're just going to keep that fear going if you don't have a go. So use a whiteboard if you want to be able to rub it out and start again, or just use an electronic version of a whiteboard, whatever app that you have that will act like one, or use scrap paper. Underline or highlight numbers. So really find all the numbers in the question if it's a long question. Tick them off as you're using them is ideal so that you can see that you've already used that number. You probably don't need to use it again. And then check. So for example, in a titration calculation, you often have 2 volumes, and a common error is to use one volume twice and the other one not at all. The other option is to use lots and lots of different chemicals, so and then confuse and actually use the same relative formula mass twice. So by ticking things off, then you avoid doing that. Even better if you can take the numbers and write them underneath the chemical formulae, because you usually have a balanced equation. If you're not given a balanced equation, you probably need to write one per question. So write it and then put the numbers underneath. Any volumes, any masses, any concentrations underneath with the units, so you know what they relate to. And the more you write down, the less your brain is having to hold on to information. So it seems odd, what I find often when I'm talking through a calculation with a student is we will work something out and they will go, yes, that's what you need to do. You need to divide that number by that number and this is what you get. And then they try and take that number, which is still in their head, and move on to the next step. But now their brain is trying to hold on to that number. Your working memory can only hold between 3 and 7, usually about 5 bits of information at once. So if you're not used to this type of calculation, if you're not writing it down, you're trying to hold too many bits in your working memory. And especially because of that, don't rearrange formulae until you're really confident. Don't just try and do it in your head, because writing it down will show you where the mistakes are a lot clearer than if you're just trying to rearrange it. The number of times I will hear a student vocalize the equation correctly. So they will say moles equals mass over the formula mass. And then they will proceed to not write that down, and then they will just put the numbers in the wrong way up. And then they're not estimating, and so they're not realizing that their number is 50 times too big. So write it down, start with the formula, see what numbers you have, put those numbers in. And thinking about it, obviously the other real reason for writing stuff down, especially for practicing and giving yourself the confidence, is when you get to the real thing. Imagine that there is a 6-mark question and that you did one thing wrong, and so your final answer will be completely wrong, maybe 1,000 out or something, maybe even 1,000,000 out, who knows. So your final answer is completely wrong. If you wrote down all your working, you will get 5 out of 6 marks because you only did one calculation wrong. It doesn't matter how ludicrous your answer is, you only made one mistake out of 6 possible steps. If you write no working down, you get 0 out of 6. And of course, actually, the more you write down, the less likely you are to make that one mistake. So definitely write it down when you're practicing and when you're doing the real thing. So just to recap, get rid of any triangles, get rid of any cute ideas that you have for trying to remember formulae. Really just try and understand what the things mean: moles, concentration, volume, pressure. The more you understand what they mean, the less likely you are to make mistakes in the formulae. Understand the units for the same reason. If you know what things are measured in, you can usually work out how to calculate them. Using estimation, just really get some ideas. Have a practice next time in your lab. Think, how much does that beaker hold? How much does that hold? How many moles would be in this? Do little calculations as you're going through. Sig figs and decimal places. So really make sure you understand decimal places is for the readings that you take from instruments, and they should be fixed for that instrument. Significant figures is for the value you get at the end. when you do your calculation, and write it all down. Write everything down with units, and there'll be more about that. Even better than writing it down is to draw it, which is in a separate video on how to handle calculations from experiments, which I recommend you watch, obviously.